Human thinking is inherently fuzzy. It relies on context and operates in a diffuse space. Machine execution is the exact opposite, a rigid, perfectly empty environment that only does what it is explicitly told. Most developers begin with a specific misconception that programming is simply the act of writing code to solve a problem. When we solve problems in everyday life, we rely heavily on intuition. We leave assumptions unstated and tolerate massive gaps in logic because our brains automatically fill in the missing context. A processor does none of this. It has zero intuition. It is strictly literal. It possesses no understanding of what you actually intend to do. Consider a standard request. Show the best candidates based on uploaded evidence. To humans, this makes sense, but force that directly into a computer and it fails. It cannot process best or evidence without explicit definitions. It rejects the input. This reveals the actual nature of programming. It is the relentless, systematic eradication of ambiguity until a literal machine can finally take action. To cross the gap between human thought and hardware execution, you must build a translation protocol, a structured funnel designed to strip away the vagueness. This requires moving past the question of how do I solve this and adopting an entirely different mental posture. Engineering reliable systems requires dropping human assumptions in favor of a new question. What explicit states and transitions must I construct so the machine can execute? The first law of this artificial environment is that a machine never touches reality. It can only manipulate representations of reality. The phrase uploaded evidence is invisible to a processor. It requires strict, quantifiable boundaries to exist at all. The machine needs explicit definitions. It needs to know exactly what the input is, where it is stored, and its default trust tier. This translation process is always lossy. By forcing messy, real-world concepts into rigid data structures, you permanently strip away the surrounding context. If that structure is weak or poorly defined, the entire system becomes brittle. Brittle code usually starts right here, with an implicit representation of a core problem. Establishing this data structure is only the first step in creating your artificial world. We have successfully translated a vague desire into an explicit structural object, but an object standing still achieves no actual computation. Software engineering must be viewed as the architecture of state transformation. Humans naturally blend what a thing is with what happens to it. A machine requires you to rip those two concepts apart. Data is the structured object you defined. Behavior is the distinct mechanical process that acts upon it. To design these processes, you have to think temporally. You start by determining the exact state of the object right before the code executes. Then comes the transformation. Explicit operations apply exact rules, mathematically shifting the internal properties of the object. Finally, you define the output state. You must know exactly what form the data takes the moment the execution finishes. Every function you write is strictly a bridge connecting one well-defined state to another. Mastering this temporal reasoning, knowing precisely what exists before, during, and after a mechanism fires, distinguishes the design of robust software from the writing of messy scripts.
To keep these transformations stable, systems require architectural constraints. The most critical of these is the invariant. An invariant is a mathematical truth within your system. It is a rule that must remain intact regardless of what operations occur. In our example, the system invariant is this: raw uploaded evidence can never directly alter the core database without passing an explicit promotion check. A human reviewer might bend a rule based on the context of the evidence. A machine cannot. It requires absolute, formalized boundaries. If a piece of local data attempts to execute a change outside its permitted zone, the system must forcefully reject the action. If you fail to enforce these boundaries, unverified local inputs will slowly degrade the integrity of the broader system state. Designing a reliable system depends almost entirely on the rigor of your boundary definitions. Defining exactly what a system must never do is as critical to its survival as writing the logic for what it is supposed to do. You now have objects, transformations, and boundaries. The final architectural requirement is designing for inevitable failure. We instinctively plan for the success path. We assume our inputs will arrive clean, perfectly formatted, and exactly on time. A processor makes no such assumptions. What if the input is duplicated? What if provenance data is missing? What if evidence contradicts current state? A mature system maps the topography for these alternative realities. When invalid data enters the pipeline, it triggers a sensor and is mechanically diverted. Instead of crashing the execution environment, the error is safely captured. Every block of code contains hidden assumptions. Leaving them unstated guarantees that a minor data anomaly will escalate into a cascading failure. Strong developers define the system's reaction to failure at the same time they define its success. True system resilience comes from mechanizing the exact response to every possible missing variable and contradictory input. Look at the scale of what emerges from a single user request. This scale of organization is what separates industrial engineering from simple task solving. You have translated a diffuse human intention into a heavily bounded, mathematically precise universe. You explicitly defined the representations. You isolated the data from the temporal behavior, locked down the invariants, and mapped every possible failure state. Every successful piece of software is a highly constrained, artificial world. Inside this space, data only persists or vanishes because of the specific rules you formalized. Nothing happens by accident. The physical hardware running this world is incredibly fast and flawlessly consistent, but it operates entirely without context. It requires small, precise truths to function. It cannot execute a vague human intention. When you structure those truths correctly, the initial human intention can safely feed into the mechanical network and produce exactly the desired result. The true craft of programming is defining the rules of your artificial world so completely that a literal machine can inhabit it and execute your will without a single point of confusion.